Our first major capacity check is going to be shear capacity. Section 8.2.6 of ACI 530. First, we're going to calculate our shear stress, so the shear stress that the section is experiencing, from equation 8-20, which is FV equals VQ over INB, which is equal to 3V over 2A for a rectangular section. And that's in comment 8.2.6.1. Where we're going to take V as our shear force, which is our P wall, Q as our first moment of inertia about the neutral axis, where Q is BH squared over 8 for rectangular sections, and I, which is our second moment of inertia over the neutral axis, where I equals BH cubed over 12 for rectangular sections. And you can see how this simplifies to 1.5 V over A for rectangular sections. If we plug our B and H values in, this can be simplified all the way down to 3V over 2BH, which is just 3V over 2A. And you can see, as an example, from our previous example of a 10-meter long abutment with 3-meter tall walls at the anchor, let's say this is a 2-tier abutment with 100 kilonewton P wall value. We can then hop down here and we'll calculate our area as 50 centimeters or 0.5 meters times 10 meters and take 1.5 times 100 over 1.5 to get 100 kilonewtons per meter squared or 4.4 psi. Notice the area is different in this calculation. Well, you will notice this area is different compared to when we talk about flexural stress in the future calculations. Instead of how we usually would take the area of a beam section resisting shear, the load is rotated 90 degrees, and the ramp wall is actually kind of acting as a deep beam. So the shear we're getting here, if we're assuming each side is supported, the shear we're getting here is going to be over the section BH, which I've highlighted here in white, versus a more normal or more standard beam section, which you'd be evaluating BD as your section resisting shear if the shear force was vertical in this case. But because it's horizontal, in the diagram I've drawn, B by H is going to be the section that is actually resisting our shear. Now, to find our allowable in-plane shear stress, so what we can take as far as shear goes, we'll turn to 8.2.6.2 in the code. And shear stress in PSI must remain under the following conditions. So condition A is 1.5 square root of F prime M. Condition B is just 120 PSI. And condition C for masonry laid in running bond, but not fully grouted. And our stone masonry is placed in running bond, which is just offset pieces, but we cannot confirm it's fully grouted. So we'll use this condition of 37 plus 0.45 NV over AN, where NV is the compressive force normal to the shearing surface, and AN is the cross-sectional area. Conservatively, we can ignore this force, because it's almost negligible for us, or we can take the self-weight of the strip of ramp cap laying across the top of the wall, which I've drawn out here. But condition A is always going to govern in this case over condition C, so there is no use in really sharpening the pencil on that calculation, because as long as it's 37 psi or greater, condition A will govern at 22.12 psi. So, given our example shear stress of 4.4 psi above, does this meet the allowable shear stress per ASD requirements in ACI 530? And the answer is going to be yes. Our 4.4 psi is less than our, not 37, but 22 psi governing value from part A. In the next video, we're going to talk about axial forces and flexural forces on the section.